It's red. Was it supposed to be red?
Yeah, but where's your clicker? I'm going to go through her bio class as they're addressing the technical difficulties.
Let me do it. Excuse me.
And then you're done.
Okay.
Anna is a faculty member in the Department of Electrical Engineering and Computer Sciences at UC Berkeley. She's also one of the key players in the Berkeley Wireless Research Center, known as SWARM Lab. She received her PhD degree from University of Cambridge in UK, and then moved to Palo Alto and was one of the key technical members of Xerox PARC before moving to UC Berkeley. And she's doing some fascinating work in wearable devices, and you're really excited to hear about some of the great work that she's doing. So no further ado, Anna.
Thank you. Well, thank you very much for the invitation to give this talk. It's my first time here, and I had a very good day. Thank you all for making my day so interesting. So today, I'm going to talk a bit about what we have been doing in my group at Berkeley towards flexible wearable electronics. And I'll have a little emphasis in health monitoring because it's we have done quite a bit of work on that. I thought I would first introduce a little bit what's the motivation, why do we care about flexible and printed electronics. I'll also introduce you to flexible electronics. There are several approaches that people have been using to achieve flexible electronics. I use one, so I'll show you some others. And then I'll talk about printing and flexible medical devices. And finally, I'll finish with some of the work that we have been doing on integrating the systems, which is a whole new can of worms. So I like to use this movie or this video that was made by Samsung, where they were explaining what's the motivation behind flexible electronics. And here they are showing a let me see if this is gonna they were showing a flexible display and a glass display. The music doesn't come out, but it has very good Korean music in the background. So here you can see flexible electronics sometimes have been associated with cheap electronics. And I really don't think that's where the value is. Being cheaper manufacturing is not necessarily going to help adoption. Flexible electronics here is very clear for displays. First, it's not breakable. For displays, for people that work in displays, you can see that as he's turning here the screen, you can still see the video going on, which when you have something that's flat, you really cannot see the image as well as you could there. This display is very bright. It has the right color for our eyes to recognize color. So there's several advantages. And here I think they make the point really nice. You can look on YouTube. The hammering is really loud, and it's a great video. So people have been spending a lot of resources and time and dedication on getting flexible electronics to work. There is the approach of using conventional materials, where you just take conventional materials that perform very well for electronics, and you process these conventional materials in a different way, such as you get flexibility. So, of course, the group of John Rogers has been pushing this area forward, where they pattern islands of very high-performance devices, and then they find clever ways of connecting these islands such that they can then stretch that electronics, or they just make it very thin so it's more flexible, more malleable. It is still breakable, it is still brittle, but it's one approach to get flexible electronics. Other approach is just to deposit conventional materials that are used for large area electronics onto flexible substrates. So at Park, there was a lot of work that we were doing on that. In Princeton, people were doing that, and there are several research labs where you just deposit amorphous silicon, silicon nitride, and all the materials that you use in large area electronics at lower temperature so that it's compatible with flexible substrates. Or you take stainless steel foil that can withstand the high temperatures, and you deposit your stack of materials on that. There is another approach that is today used in commercial devices, which was developed by Philips. It's called Epler, which is, oh, you can't read there. It's electronics paper by laser release. And this process is actually used on the Kindle. The Kindle backplanes, the Kindle displays that we have are done by this, where they deposit high performance amorphous silicon backplanes onto glass, where they have a layer that is released once you shine laser. So they release that layer, deposit on flexible substrates, and then they use ink, which is electrophoretic media, as the display media, which is also flexible, lightweight. So if you pick up the Kindle and the iPad, you will see that the Kindle is much lighter. It's because there's no glass on Kindle, in the Kindle display. And that's a technology that is used today, commercially available, but the product is not flexible because everything around it is not flexible. And then there is the approach that is the approach that I have been working on in the past many years, which is to use completely different materials. There is no silicon in this approach, where you just use materials that are flexible by nature, such as polymers, and these materials behave as semiconductors, and they are semiconductors, organic semiconductors, and then you use dielectrics and silver nanoparticles or metal nanoparticles to build the layers that you need for electronic devices. So over the years, we have been working very hard to get the tools of electronics, which are the devices, the basic devices, passive and active devices. And the advantage, or what I like about this approach, is that you go away from photolithography, which is a very wasteful patterning technique, because you deposit materials everywhere, and then you deposit photoresist everywhere. You go through the process of photoresist, and then you etch what you don't want. In printing, the idea is you only deposit the material where you need the functionality of the material. So it's an additive manufacturing as opposed to subtractive. It has disadvantages, of course, because photolithography, you can get really high resolution, very small features, very nice alignment layer to layer in the nanometer scale. In printing, we are in micro scale. So the feature sizes are about 30 microns. The spacing between two features is about 10 microns. The alignment layer to layer is about 5 microns, 1 micron if you have a very good printer. So it's a different idea, and of course, if I try to use printing to do something that photolithography does extremely well, I'm not going to succeed. So it's much better to use printing and different materials on applications where the conventional way of doing things is not coping, such as large area and other things that I hope I'll convince you today. So this area has been a materials-driven technology area, where for many years it was dominated by chemists and physicists. Chemists making new molecules every day, physicists studying the transport properties of the semiconductor, and then the more adventurous physicists trying to show the applications. So the applications were kind of limited per se, but they were really huge markets. So there was a wave of materials that came that was for OLEDs, organic light-emitting diodes, which was really the area that brought light to this area, because the materials do emit light much, much better than conventional materials, than inorganic materials. Much more efficient, and the color spectrum is much larger than what you can achieve with conventional solid states. Then it moved to the era of transistors, film transistors. All the chemists were doing film transistors, materials, and then eventually we went to the solar cell energy. So there were lots of materials for solar cells. And that's great, because it means that today we have very good materials that emit light in all colors of the spectrum. We have materials that show decent field effect mobility, nothing like high-speed electronics, but decent, better than amorphous silicon. And we have materials that are very efficient absorbers. So with that, you got the basics of electronics right there. So another movie that I like to show, this movie was given to me by my good friend Paul Blom, who is now at the Max Planck Institute. But here he was working at the Host Center, a research lab for Philips, where they have the goal of making the next generation lighting, Philips. So here is an organic light-emitting diodes emitting white color very efficiently. This was patented on a flexible substrate, on plastic substrate. For those of you who work with organic light-emitting diodes, you know that LEDs are very current-driven device. So in a large area like this, you have a huge current going through. But there you go. It's a flexible substrate. So they designed this big pixel, or this big light, in a way that you could cut the LEDs in different shapes. And they had a cute name for this, so it's the illuminator. And the idea was that you would have tapes. You would buy a tape or a roll, and then you would cut the LEDs in whichever shape or form you want to either decorate, or this was just a cute thing to show. But it shows the potential of the technology. So you see there, they cut it in half, and then they give the power supply back, and the LED is working nicely. And now you see that the researcher gets encouraged by the experiment, and now he is going to cut this LED once again in half, and you see that it keeps working even as he cuts. So these devices are fabricated in a very simple structure where it's just a sandwich. In the simplest structure, is a sandwich between two metals and the polymer, the semiconductor that emits light. So as he cuts, it shorts the edges, right, because of the two metals. But if you increase the current, you get rid of those shorts, and there you go. There is a defect right there, this place. So you see that it's working. So this is the point. It's to do electronics differently. So in my group, when I moved from industry to the university, I had the pleasure to start working on new areas with students that didn't know what they were getting into. And we really fought really hard on where we really need flexible electronics. And where do you really need to print? Because, okay, I loved printing technologies, but is there a space? So over the years, what we found in several applications is that if you have contact with the human body, electronics, human body, flexible electronics makes sense. Because the way we design electronics is really not compatible with our bodies. Look at the microphone, right? This is not integrated with what I'm wearing in any sense. I don't wear my cell phone because it doesn't fit my pockets. So the way electronics is designed is not to be in contact with the human body. But humans use the electronics all the time. And then, so we said, okay, so let's work on medical devices. And this was really before wearables became a thing. But I love the fact that wearables became a thing because they helped my funding. And wearables are not such a good thing anymore. But we decided to work on medical devices. And what we found was that in several applications, if you bring the electronics close to the body and you design the electronics to fit the area where you want to take that measurement, you get a gain in SNR. So your signal-to-noise ratio goes up, and the comfort of the patient that's using that electronics also improves. And when the patient feels more comfortable, the patient wears that for longer, and the patient is behaving more like the patient would, as if there was a big block of electronics poking them. So we have applied this concept to MRI, for example, where we were printing the RF coils for MRI, and we found, because right now the way MRI is done, you still have to go in that big magnet, which several people are very afraid of going. But in order to capture the signal, you need to have these RF coils that are placed in your body. And they're very, very heavy. So here you are already scared of going inside the tube of the scanner, and then the doctor puts something really heavy in your body that is actually squeezing your lungs. So of course you are going to feel claustrophobic when you're there. Or if it's a head scan, they put a cage right here in your head. So a colleague of mine who is a specialist in signal processing and parallel processing came to me and said, Anna, the biggest problem in MRI is actually the coils. Can you print the coils? And of course, I had no idea what coils were about, but I learned. I'm at university, I learned. And we have shown that this can give better image when you compare to what's used in the hospital today. That even though we are printing 3 layers on a plastic substrate, we get better performance than the really high performance GE coils or Siemens coils that you can buy today. Today, that technology has been tested, especially for pediatric patients at the Stanford Children's Hospital, and we even decided to open a company to commercialize that. All because it's fitting the body. The other example was just a simple array of bioelectrodes, bioimpedance electrodes that we applied to monitor the formation of pressure ulcers for patients that are in the hospital for very long, for extended periods of time, or the diabetic patients where the method that is used today to monitor the formation of pressure ulcers is a nurse going there and looking to see if the skin is turning purple. And what we've shown is that if you actually measure the impedance of the skin, you can pick up changes in the impedance 2 days before it's visible to the eye. We also shown in our study that if you only pick up the pressure ulcer when it's visible to the eye, there is already damage that is not going to be reversible in the tissue. While when we pick up the change in impedance, the damage is reversible. Yes?
What kind of resolution do you get of those?
Those is not. Okay, the question is what kind of resolution we get in the sensors. So the resolution that you need is not very high. Those are 64 electrodes, and the array is about this big. And we just do the nearest neighbor measurement, so we can create a very nice map. If you go to that publication, there's a lot of detail there. While ulcers are normally in a bigger area, so it doesn't need to be very high resolution, which is a good point. So, photolithography it would be an overkill there. And then finally, monitoring vital signs, which I'm going to talk a little bit more about it. So, the message here, what we the way we are looking at electronics or wearable sensors is that we really need to go away from the mindset of one size fits all, because we know that one size doesn't fit all. So if you have a technology where you can print millions of pages of content that is completely customized, which is the printing technologies, why don't you use the same to electronics or to electronic systems, where you only put sensors that system really need. You only put the computational electronics that's needed for that application. You design for the right power, and then you print the right battery, and everything is integrated in a way that you can wear, and it fits the application, it fits the person, it fits the purpose, as opposed to just design another black box, sometimes silver. Moving towards the health monitoring, when we started this work, our idea was we always focus on the medical devices, and the idea was that when you're checking into a hospital, they print out a label that they put on your arm with your name, maybe your blood type, the day you were admitted, some information there. And that is disposable. You wear while you are in the hospital, they cut it up, and off you go. So we thought, okay, if they are already printing that, why not print something inside that band that will be monitoring a health sign, all your health signals, or it might even be monitoring your motion, controlling or having an idea where you are in the hospital. And we even had this nice concept where that the button could be a button battery, and you could power things like that. As we moved, we got Intel very interested in this, and we had a nice project with them. And then we started looking at where else can you wear a sensor and still get the biosignals that you want to measure. So we looked a lot on where to place the sensors in the body. And by looking at where to place the sensors in the body, we also looked which kind of sensors would make sense. And then eventually at BWRC, we came up with a project that's called the Human Intranet, where we look at wireless technology as well as the sensors to see how the sensors will be communicating with each other if they are placed in different parts of the body, and how the sensors will be communicating with the conventional electronics. But for us, what we had in mind was that our flexible sensors were lightweight. We had the ability to fabricate them in different sizes, cover different areas, different resolution, and we always got higher SNR in all applications that we looked at. So, but we are engineers in the end of the day, and it's very hard to for an engineer and for me to understand what are the biosignals that you have to measure. And we spend a lot of time trying to learn that, and then we came up with this table that it's a bioengineering for dummies. No, for electric engineers. Where if you look at the biosignals, these are pretty much, they covers a lot of the biosignals that one could measure. Then what type of biosensor, or what are the methods that you would use? There are several methods that one could use. There are some that are electrochemical, some are optical, some are just resistance that you're going to measure. Then you look at the signal. The signal is always a resistance, a voltage, a current, and that's pretty much it. So that's good. We start getting more comfortable here. Then you look at the measurement range, of course. That's where your design comes into play. Can you design something that will be wearable, flexible, and cover the range that you need to cover? And for those who worked on printed electronics before, one thing that printed electronics is always criticized by people that work on silicon electronics is that the frequency is very low. And I never had a problem with it because I know the frequency is low, and I'm looking at things that I don't need high frequencies. And biomeasurements are very slow. They do not require high frequency. And you can see here the highest frequency that I have on this table is 10 kilohertz for EMG. And I'm very happy to say that we've done EMG. So I think printed electronics can deal with bioelectronics. It can be bioelectronics. So I'm not going to talk too much about printing. I'm not going to talk about the technique. I'm happy to answer questions. And as I go, I'll tell you which printing technology we were using. But basically, we mix and match the printing technology depending on what we need, which kind of patterning we want. Inkjet printing is a digital technique, so it's very useful for customizing your design because you can change the file very quickly and then you print something different and you say, oh, this connector is not good or this is a weak point. You go, you change your design and off you go. You have a new design. So we use a lot of inkjet printing. We also use a lot of screen printing because the screen printing is so easy. My student built a screen printer for $100. And you buy the screens from shops that are making silk screens for T-shirts. And then as you develop the relationship with them, they become interested because you're printing electronics, and you can actually get screens that are quite good, and the resolution is about, you can get 50 microns with screen printing, and quite high, quite thick film, so you can get good wires, let's say. With screen printing. And we also use a lot of blade coating because these materials, especially the semiconductors, they are somewhat low viscosity solutions. They are sometimes they are with organic solvents. They're dissolved in organic solvents. And the technique is very simple, where you just wet a blade with the meniscus of your solution and you spread that solution over a substrate. It's really just like spreading butter on bread, but more exciting. And then when we need the and when we need the high performance electronics, when we need wireless communication, or for the sensors that we want to do some computation close to the sensor, we use a silicon chip. Because it works so well. Okay. So let me switch to the sensors and to the vital signs.
I have a quick question based on that. Is there, why is there no kind of multi-user boundary that I can send off to get flexible electronics? Or is there that I'm not aware of?
Thank you, Sarah. This is, the question is, how come there's no central printing place that I can just send an order and get what you want? This is my dream. My dream is to have a printed electronics shop. Just like you go to a graphics and you can get a wedding invitation, you can print a catalog, or you can print exams. In all that print shop, all you select is the type of substrate, the color, the quality. Why not do this in printing? We're not there yet. The missing piece, I think it's, are we recording this? Because I might offend chemists. I think it's because the area was really driven by chemists for so long. So it has so many materials. Then I get my electrical engineering students, and they look at all those organic molecules, and they say, I can't work in this area. You know, there's no recipe, there's no procedures, so the area is shifting a little bit, and all the publications were about the highest efficiency, the highest mobility, the highest, and then you can't get the highest mobility all the time. And then how do you convince that student or that company or that investor that it's okay to have a mobility loan. So we are getting there, I think. There is a center called NextFlex in San Jose now, and their goal is to have manufacture of printed hybrid electronics. And so I'm hopeful. Yes?
I have a follow-up question. Do you see any convergence of specific materials at this point, like the specific formula, the general formula across multiple groups we're going to want to use for a wire versus
a little bit. I see conversion. Do I see? Are there people online? Oh, good. So, so there is, do I see conversion? Is there conversion of which kind of materials? I always push that printed electronics should have a workhorse material because that's what made silicon so successful. Everybody worked with silicon, not with different materials. I see conversion on the metals. Printable metals, you don't have many options. So people were trying silver and copper and gold, and now silver is pretty much mainstream. And there are formulations for screen printed silver. There's formulation for inkjet printing. There's all sorts of formulations of ink that you can buy by the bucket, which is great. And then one of the criticisms that silver nanoparticles or metal nanoparticles had, especially when you think about row-to-row manufacturing, was that you have to anneal the material. You have to sinter the nanoparticles in order to have the conductivity that you want. And those methods are mostly thermal annealing. And the recipe is coming from research labs where, you know, oh, you anneal at 150 degrees for half an hour, or you anneal overnight, you know, recipes that students conveniently find. But I always had recipes overnight, so I'm guilty too. And now there is actually companies that are commercializing not only the printing equipment, but they commercialize the ink and the curing machine, where there is, for example, a company that's called Novacentrics, where they have a very nice light curing, a very high power light that cures the silver ink in a question of seconds. So that becomes more feasible. In the semiconductors, there is not really large conversions. It's still, you have to have a very good friend who's a chemist who makes you more materials than they would make, and yeah, but we're getting there. In the organic light emitting diodes, it's much easier to get materials by the bucket, yeah. Okay, so moving to wearable sensors. One of the vital signs sensors that we wanted to develop, or that we have developed, is a blood oximeter. Because a blood oximeter gives you information about your pulse rate, but also gives you the information of oxygen saturation in the blood, which is an indicator of how healthy you are, how well you are. And if you can pick up changes in blood oxygenation, you can look at trends, and if there's a trend in your decay in blood oxygenation, or if that's related to a certain activity that you do. So it's a very good indicator. And today when you go to the doctor, it's one of the first devices that they clip to your finger. Before they measure temperature, they put the blood oximeter in your finger. So everybody knows that. It puts in the finger and it clamps into your finger. And the reason it's clamping is totally packaging to make sure that it's blocking the outside light for interfering in the measurement. And this measurement is done with two LEDs, two light sources, and one photodetector. The light goes through the tissue, through the finger, and the current, you measure the current in the photodiode on the other side. And the reason you can calculate blood oxygenation out of this is because there's no laser pointer, right? Oh, I'll use my mouse. So it's because if you look at the molar extinction coefficient in the blood, there is a difference in the absorption between the venous blood and the oxygenated blood. And this difference in absorption is quite substantial around the red, quite big around the infrared, but there is also differences in other areas. So here, if you look at the ratio between the absorption of the oxygenated blood and the venous blood, you can see that there are several areas where you could pick up that ratio, that difference. So that's the first step in performing this measurement. You have to pick the wavelengths that will give you that ratio, or the highest possible. And then you compare to the ratios that you get in two wavelengths. In terms for the electrical engineers here, when you are measuring pulse oxygenation, you have pulse going, and that's the signal that you want to pick up. But the light is also going through bone, through tissue, from blood that's not pulsating blood, and all that contributes to a DC signal in your measurement that is quite large. And then you have this little AC signal oscillating on top of the DC signal, which carries the pulse information. So for pulse oximetry, you have to pick up this AC signal. If you don't want pulse oximetry, you just want to know saturation of oxygen in the blood, then you can measure in other locations where you don't have the pulse. But you always need the pulse to calibrate your measurement, and I'll go back to that later in my talk. So we went back to organic electronics, and since people worked so hard to make nice displays, which by the way is going to be in the new iPhone with these materials, organic materials, we picked red and a green LED. Mostly because there were no infrared material available when we started working on this. And then we developed a photodiode that has quite broad absorption, and the photodiode could pick up signals in both wavelengths. So you can see here that the wavelengths are in places where there is difference in the blood. So of course, we were the first to show that this could be done with organic devices. So we had to compare ourselves with solid-state electronics, where in the first comparison there we have the organic photodiode and solid-state LEDs. And you can see that we can pick up the PPG, the spectrum there for green and red. And then we swap, we use organic LEDs with a silicon photodiode, and you can still resolve the pulse. And then when we put the two organic devices, you resolve the pulse. The difference is in the magnitude of the measurement. And the magnitude in the measurement depends on the area of the photodiodes, the area of the LED, and many aspects. But the important thing in the measurement is really the ratio between the two signals. So if you can resolve the PPG, you can calculate blood oxygenation. And then we worked with a company in England, the company that was actually making the materials for the LEDs. And we went and demonstrated I think that for academic standards, this is pretty good demonstrator with a flexible oximeter that is there around the finger. We have a nice box that does the measurement connected to a computer, and then it will display there the measurement. Okay. When we compare this to commercially available sensors, the error in the measurement that we see is about 1%, which we really think it's just the error in the measurement, not related to the device itself. But if you read papers in organic or printed electronics, the motivation is always, oh, you can you can scale the area, you can do large area. And it's true, you can do large area. And here we showed that if so the signal in this measurement is the current that you get from the photodiode. right? This is your signal. So we show that if you increase the area of the photodiode itself, you increase the current in the photodiode. And if you increase the active area of the OLED, you also increase the current in the photodiode. So that is increasing your signal. And then, because we could flex those sensors, we showed that the noise, which is the ambient light in this case, if we flex the sensor and compare the ambient light that is picked up by the photodiode, you can see that you reduce significantly the error in the noise and the measurement, which is the ambient light. So that's why we get good SNR here, because you increase the signal and you reduce the noise. But this was not what we wanted to do. We didn't want to do a transmission mode oximeter that would compete with what they have in the hospital. We wanted to measure by reflection and be able to wear it in different parts of the body. So that's where we took the research next. Measuring blood oxygenation in a different mode, where now the light has to interact with the blood and be reflected back, and you pick up the signal that is reflected back. So it's a more difficult measurement, but because you can play with geometry and play with area, play with flux, and because of the technology we are doing, we were quite successful, and that's what I want to share with you now. So by then the funding was coming, so we had several concepts, and one of the projects that we had with Intel was to have a multi-sensor platform where we had the blood oximeter, we also had thermistors, and then we also added some of the chemical sensors here to monitor analytes in the sweat. I'm not going to talk about the sweat sensors because they are by themselves a big talk. So I'll keep going on the integration and the reflection mode. But here's the concept, and here's how far we went, where you can see where the bottleneck is in flexible electronics, because we still have a PC board there that is not flexible and it's squared and pokey. But we have the flexible here blood oximeter that operates in a reflection mode, and then the sweat sensors are on the other side. It's a bit dark, you can see, that was monitoring both. And of course, then the students developed an app that's called WearX, where you can add sensors, and it communicates with the cell phone, and it gives you the numbers from all the sensors. But so in terms of fabrication, just to give you an idea, here we use blade coating for the OLEDs and for the photodiode. We use inkjet printing and screen printing for the sweat sensors and for the thermistors. So a mix of the printing techniques. One thing that we also have done was that when people talk about row-to-row manufacturing, they say, oh, wouldn't it be great, you start with a row of empty plastic and you end with a row of functional devices. And I think it would be great, but it's very, very hard, because normally people look at the position of one material and then the position of another material, and then you have to align somehow. You have to take the roll and go back. And so here we looked at, could we just print two OLEDs at the same time, and these two OLEDs have different colors, and they are already spaced at the space that we needed for the application. So here's the customization part once we knew. And the answer is yes. And I would tell you even if the answer was no, but in this case, yeah, it's yes. And we compared the performance of these printed OLEDs together in the same time with the printed separates, and they perform just the same. But what we wanted to do was really to measure oximetry. So here's the prototype, and and the measurement. So you can see we can resolve the green and the red, and then the third curve there is the signal that you are getting. We need to resolve the peaks and valleys. So we can pick up the peaks and valleys, and then we get with the peaks and valleys, we get the heart rate. And then with the ratio between the two signals, we calculate the saturation, the oxygen saturation. So, okay, so that's a nice result. How did we get there? We had, of course, to design the sensor, and for the design, we fall back to the solid state, and we made a board where we had an array of photodiodes here, and they were placed at a predetermined distance from the light sources, and then we measured. We changed the flux on the LEDs, and we changed the distance of the photodiodes. We changed the sensing location as a forearm here and wrist. Today we have actually measured this in 8 parts of the body. And then we introduced infrared, because by then we had convinced that company CDT to make infrared materials for us. So now we have infrared emitters. And you can see here that no matter what you do, the infrared gives a better signal, which for us, it was not obvious at the beginning, because we thought since infrared goes deeper into the tissue, we thought that infrared would give us the weakest signal, because we wanted reflected light. But actually, now that we worked on it, it makes more sense that infrared would give the stronger signal, because it goes deeper and it also reflects. But and then you see that between red and green you don't see a significant difference in the quality of the signal, but infrared is really a plus here. And the distance between the emitter and the photodiode is about 0.5 centimeters, which goes to show that the resolution needed in this patterning is really not high resolution. Yes? Yeah, he's asking, I learned, he's asking how deep would infrared go. I don't know the number. I haven't found a good way of measuring it, but we can tell that it goes deeper enough to get the artery and to get the signal from the artery.
The reason I ask is that for these sensors of somebody doing exercise, it might be interesting to know the underlying condition of the muscle, whether it's anaerobic or anaerobic.
Yeah, it would be interesting to do that. And that's where the sweat sensors play a role too, because from the sweat analytes you can tell about muscle growth as opposed to muscle suffering. Yeah. Okay. So okay, after all this design and fabrication and so on, we got sensors that perform really nicely in the 3 colors and through reflection mode, which we thought it's a great step forward towards wearing a medical device or a device that will give reliable results. Then comes the question, how do we know the device is really working? Because we only measure in healthy people with the transmission modes on the finger to calibrate. And then the question we had was, can you measure trends? Can you measure the change in the saturation, which is the only point that you would wear an oxygenation sensor all the time? And then it turns out that we have the students that does training for biking at high altitudes, and this guy sleeps with an oxygen mask where he keeps his oxygenation levels at 90%. And he said, oh, you guys can just buy the mask that I use and you can do this. And that's exactly what we did. It's incredible that you can do that. I didn't know about that. But you can vary the oxygenation level very rapidly and in a very safe way. And then we came up with this experiment to test this. To give you an idea, a person that suffers from respiratory disease, their oxygenation levels go down to 80%. While normal people, healthy people, it should be 98%, 99%, close to 100. So here we were staying in the safe part, okay? So we only stayed to 90%. So the experiment that we did was that we have the transmission mode, and you see we haven't published this yet, but I'm happy to show here. So we have the transmission mode in the finger, and we have now the reflection mode is in the forehead. I don't know why, but I think it was the best way to integrate with the student wearing the mask. And then what we are doing here, we are varying the oxygen levels through this mask, and we are tracking the signal that we get from the red, from the infrared, and here we are computing the saturation. So you can see here that when we set in the machine to change the oxygenation, there is a fast response that you get from both sensors. Here's the reflection printed probe. And then when you get the oxygenation to go back to normal, you see the rising of the oxygenation. So with this, if you look here at the time where the oxygenation was coming to a low point, you can actually pick the trend here in the signal very clearly for both sensors, and then you calculate the oxygenation, and you see that the difference in the calculation is very, very low. Okay, so where are we going now? We are making arrays of these oximeters because if you have a sensing modality where you are taking data from one sensor, of course your data is not going to be as reliable than if you have data from several sensors that are placed in the same place. And for motion artifacts, if you have an array of sensors that is now in your wrist, let's say you move and you lose the artery from one sensor, you can still pick up from others. So arrays have the redundancy, the data redundancy advantage here. But we also want to monitor and map oxygenation of tissue in general. So let's say if you have surgery and you need to monitor how the wounded area is recovering, then you can place this over the place where you had surgery, and you can monitor the oxygenation there. You can also monitor temperature and the impedance in order to have an idea or to monitor how well you're recovering, as opposed to have someone open and look, to remove the looking and deciding if it's good or not out of the picture. So we are moving in that direction. We have arrays of bioimpedance, and now we are working on integrating the blood oxygenation with bioimpedance to monitor wounds, essentially. And for that, we are funded by NextFlex, which is this manufacturing thing. So here is just to show you this is just showing variation that you get in of signals on the wrist because of this motion. And that's why Fitbit and many of the wearable devices that you have don't work very, very well. And sometimes you are exercising and then all of a sudden you don't have pulse, but you can keep going. All of that. It's because it just loses from displacement. So here, if we have an array, then you can see how you can cover that area much better. So this is one of the, as I said, it's the place where we are pushing this, where we have multi-pixel measurements. Okay, and it's 5 o'clock, so I will stop here. And of course, I have to thank my students a lot of the work that I showed today was done by this student, Yasser Khan, who is graduating in the spring, and he's going to be applying for faculty positions. So if you like this area, I would recommend no one stronger than I would recommend this guy, and I'll cry the day he leaves. But he's amazing, so I have to give him the credit for this work. And of course, the people that fund, thank you very much. And thank you for listening on a Friday afternoon.
We have time for a few questions.
Yes.
Thank you. I have a question about array for LED. Does your light emit light that is it also somewhat does it affect like how do you isolate?
Yeah. That's a very good question, and I will repeat. He's asking if the light emitted by the LEDs is picked up by the photodiode before it interacts with the body, right? If it interferes, essentially. And the answer is yes. So if you bring the two LEDs too close together, they will interfere with each other in the measurement. So that's the reason we did that study on the distance, to maximize the signal with the distance from the photodiode. In some of the wearable devices, if you have one, none of them measure blood oxygenation. They measure pulse, and they have only one color. I think the Samsung device has several colors, but still, what they do, they put physical barriers. So they have this black plastic between the LEDs and the photodiode. Yeah, you have one. So you can look, there's this black plastic that is isolating it. And it works really well if you really stick that device to your wrist, right? So if you have the mark of the device on your wrist, it was working really well. But otherwise it doesn't, because it's really close together.
Done any accelerated lifetime?
Yeah, people have done accelerated lifetime testing for LEDs, for photodiodes, because of the solar cell and the TV application. Because the need there is lifetime of 20 years, right? If I buy a TV, I want my TV to last for very long. These devices, they don't need that. The lifetime of medical devices is about 7 days maximum. Okay, so it's a completely different business proposition. Wearable devices, the lifetime is 2 years. So I haven't done that type of accelerated testing, but we did do the measurement for 7 days without encapsulation. And because what you want is the ratio, and the devices that degrade the most are the OLEDs, because it's high current and they have a low work function material in the stack. And up to 7 days, we could still do the measurement. There was a little degradation, but you could still do the measurement. So all of a sudden, all these people that are trying to make OLED TVs are also interested in medical devices, because it's a completely different proposition.
For doing the, I'm sorry.
We'll go back. We'll go back.
Yes. For comparing your sensor to the conventional, what's the power difference for doing the same operation?
Oh, the power consumption.
Yes.
Yeah, the power consumption, there was not much of difference, because the LEDs, they both use a lot of power. The solid state green LED is slightly more efficient, and I believe that's why they use the green LEDs for all the wearable sensors. But it wasn't that different. But the most consuming component is the LED, And then if you add wireless, if you add Bluetooth, then Bluetooth takes everything.
So your concept picture of the pulse oximeter on the finger didn't have any wires connected to it. Which concept? The concept picture with the pretty lights on the finger, right, wrapped around the tip of the finger. So.
Nature communications.
Well, I know. I've got no problems with that, but flexible batteries, you must be.
Oh, thank you. Yeah, I could give a talk about flexible batteries. We work a lot on flexible power sources. And the project with Intel, we actually did have a watch with Intel where it was much thinner because the sensors were thinner and the batteries were on the bands of the watch. So, and then for that, we calculated the power needed for operation of 1 day with a certain data acquisition and data transfer rate. And then we designed the batteries to provide that power without needing recharging for the whole day. Yeah. So we did go in that direction. Yeah, there is a big chunk of my group. There's Ala, Abhinav, Kartik. So lots of people here that work on power. Baltazar works on power. Yeah, thank you.
Okay, let's thank our speaker one more time.
Thank you.
It was a record Friday afternoon.
I did. Oh.
Such a great attendance.
Oh, it was such a great visit. Thank you.
You did a nice job.
So I knew you.